Hello everyone. I'm Srikanth, and the title of my presentation is Enabling Precise Timing Control in SDRs. I'm going to start off by providing some motivating examples where having precise timing control is an important prerequisite in order to implement the subsequent signal processing algorithms. I'm going to talk about the ADRV9361 Z7035, the RF system on module architecture a little bit within the context of the problem that I'll be describing. I'll talk a little bit about the loopback delay estimation algorithm itself, and subsequently the reference design where we implemented this algorithm and some performance results to conclude the talk. So when we think of having precise timing control, two very important examples that come to mind are radar and the context within which this particular implementation was done, which is power amplifier digital pre-distortion, which is of course a very pertinent problem, something that has attracted quite a bit of attention when it comes to implementing using software-defined radios. Because we are solving more and more analog problems recently in the digital domain using digital signal processing algorithms. To go into a little bit of detail concerning digital predistortion and where loopback timing delay fits in this context, if we think of the transmit waveform as, let's say, the LT5 compliant waveform, its bandwidth is going to be 4.5 megahertz, and the mandated samples per second sample rate is 7.68 samples per second. But typically, we want to oversample this signal because in the context of digital predistortion, we want to look at the ACLR values in the first adjacent channel on either side and second adjacent channel on either side. So that requires that you oversample the signal 5 times. So that gets sent to the transceiver and eventually to the power amplifier, and by way of a coupler, it is fed back to, say, the host PC or the Fpga on the zinc SoC sitting in the RF system on module that actually implements the digital predistortion algorithm. So if we see here, the digital predistortion algorithm, it requires both the reference waveform and the received waveform, but they need to be aligned in time in order to do the DPD adaptation and actually linearize the PA effectively. So studies have shown that any mismatch in timing delay between the transmitted waveform and the received waveform, it results in suboptimal DPD adaptation, and the ACLR for the signal of interest is going to be insufficiently suppressed. We don't want that. So in this context, in order to conduct this loopback delay estimation, we used a particular feature of AD9361, which is using the TX power monitor pin in order to observe the transmit signal. So one important aspect of the TX power monitor pin is you can only use it in TDD mode, because clearly only in TDD mode you have the receive chain setting idle, and it is able to observe the transmit waveform in order to do loopback timing delay estimation and subsequently feed the waveform to the downstream stages. The other point is TX power monitor is multiplexed into the receive chain after the LNA, so the LNA is bypassed because obviously the transmit waveform is going to be more often than not, its signal level is going to be pretty high. So we would like to protect the receive chain. And importantly, the local oscillator signal that is used in the transmit chain is the same local oscillator signal that is fed to the receive chain also, because we would like to limit the problem to only loopback timing delay and not worry about the phase offsets. So to talk a little bit more about the architecture of the RF SOM, my colleagues have gone into more details regarding this slide, this architecture, but I'll spend a few minutes. So whether it is FMCOMs or whether it is Pluto SDR or the RF SOM, the architecture is pretty similar. You have the transceiver here, which communicates with the kernel drivers in the embedded Linux on the ARM. You have Lib-IO that is talking to the transceiver as well as to the host application in order to configure the transceiver and perhaps capture data and perform signal processing, etc. The kernel drivers also talk to the AD9361 Hdl IP, and perhaps there is some custom IP that is also able to do the signal processing on the samples received. But the most compelling use of Zinc SoC, as we know, is to have it untethered from the host PC and to do all the signal processing on the Zinc SoC itself. So in order to do that, in our implementation, what we did is we implemented part of the logic using Simulink and HDL coder workflow in order to generate the IP. So that makes these MathWorks IP core devices available, which are also accessible through Lib-IO, which write some values to AXI registers, and those registers are accessible whether the application is running on the host PC or on the ARM itself. To go over a few details regarding the design flow, this is a pretty common design flow across comm system design, where you typically spend a significant amount of time initially on the research and algorithm development pieces, and subsequently the big piece is design elaboration and prototyping. Maybe you have the algorithm developed and its functional characteristics evaluated in floating point. Subsequently, it is converted to fixed point implementation, and following some optimization regarding the bit widths of various variables involved, we convert it into HDL code and target an FPGA. This is the same design flow that we used also, but as far as algorithm development is concerned, we chose a very straightforward algorithm from the published literature. So this algorithm for estimating loopback delay is a straightforward correlation-based approach. We first take the input signal and the feedback signal and compute the amplitude difference, which is nothing more than taking the signed amplitudes and computing the difference between the reference signal and the feedback signal. Subsequently, at this point, because the resultant signal is going to be simply ones and zeros, that is binary, we can implement the correlation using XORs rather than using a filter, and that makes the computation pretty straightforward. And finally, what we have here is a simple local max finding algorithm. We feed a particular threshold, and it finds the local max and the index associated with that value of the correlation function to give us the value of the integer delay. So some more details regarding the HDL code that we generated using Simulink HDL workflow advisor workflow and the GNU radio flow graph that actually implements the fractional delay algorithm. What we see here is we write a value to an AXI register, and that kickstarts the process of sending a pulse waveform. The pulse gets accumulated over time, and that forms the indices going into a lookup table. The lookup table consists of samples from an oversampled Z of choose sequence. That waveform is sent to the transceiver, and using the RF loopback, it is fed to the receive input port of the transceiver. So the integer delay estimation block receives both the a reference waveform, which is looped back within the IP itself, and the RX waveform. So that computes the integer delay, which is fed to this align streams block. A status value gets written, which says that the integer value has been computed, and the custom IP source in gr-iio flow graph, it reads that register value to start the process of estimating fractional delay. And the final block here, the correlator, it writes the value of fractional delay as well as a status value that fractional delay is now available for the IP to correct for fractional loopback delay. So in this way, the two pieces communicate with each other. Now some more details regarding the reference design. As I indicated earlier, this is a particular workflow where the algorithm is first implemented in the host PC, then you move from the host PC to distributing the different pieces of the algorithm to the ARM and the FPGA. So to start off, the delay estimation algorithm, both the fractional piece and the integer delay estimation piece, they are in the host PC. This custom IP, which is shown in green, is where we would like to have the integer delay located, and that is in the data path between the DMAs and the AD9361 HDL IP. So in this step 0, the transceiver is only acting as a streaming device. We send all the samples back to the host PC, and all the signal processing is done on the host PC by way of embedded Linux, Lib-io, etc. The next stage is to move the integer delay estimation from host PC to the FPGA. So as you see here, the path estimation, which is in fact the integer delay estimation piece, takes two inputs. One is the reference waveform, and the other is coming from the radio. It aligns those streams, but at this point only the integer delay has been corrected for. So it sends those values to the host PC by way of Lib-io API and the ARM. And on the host PC, we correct for fractional loopback delay. The next step is to have the gr-iio flow graph, which is sitting in the host PC, and move it to the embedded Linux on the ARM. And the value of fractional delay that is estimated is written to a register, and the fractional delay correction block, which is nothing but a Faro filter, a third order Faro filter, reads that value and corrects that value so that the two streams which are now aligned are available for further processing. So we then conducted some measurement results using this implementation. We took a few cables and looked at the expected value in terms of the loopback delay and the observed value. The expected value is simply based off of a theoretical formula which takes into consideration the dielectric constant of the cable, the center frequency of the signal, etc. And we noticed that our observed values were tenths of microseconds off from the expected value. We hypothesized that perhaps the propagation delays through the DSP, the on-chip interconnects, were adding a delta value to our observed loopback delay answer. So subsequently, another study that we conducted is we ran this experiment across an extended length of time, because this ties back to our power amplifier digital pre-distortion task, within the context of which we are evaluating this loopback delay implementation. What we observed when we ran this study across a wall clock time of 4 hours is the integer delay remains constant. And when it comes to fractional loopback delay, we observed that more often than not, the fractional loopback delay is one of two values. So in this particular case, we observed that it's either 10/16 or 11/16. 16 is the oversampling factor that we used in order to determine the intermediate fractional delay between two samples. We also notice that sometimes the value is very different from these two peaks that we expect to see in the histogram. We hypothesize that perhaps because of the temperature gradients that are going to occur invariably when you run a chip for a very long amount of time, those are causing these other estimated values. The other important thing is we looked at the length of time over which the fractional delay can be expected to be constant. And that number corresponds to anywhere between 10 seconds to 60 seconds. What that means is, tying this back to the DPD task, it means that that is the length of time, or that is the time scale over which the DPD needs to adapt its coefficients, because the behavior of the chip itself in terms of introducing some delay has changed over that time scale, which is of the order of seconds. And it is significantly longer compared to the number of samples that we might process or the number of packets that are received for a real-world standards compliant waveform. So this tells us that the DPD algorithm needs to adapt over a time scale spanning seconds. That's the conclusion that we got from this plot. And that concludes my presentation. Please let me know if you have any questions.